covalent chains, molecular structures. First one, there are different types of chains, right? First one, linear. Okay, linear. So probably we will have like a kind of carbon, 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 like this, right? Maybe we will have hydrogen, hydrogen, hydrogen. So this is what called linear, right? If I have a polymer like this will come under this category. All right. Then branch, right? Branch. So if you see, for example, the one I told, like 2-methyl, 4-ethyl pentane, right? So 2-methyl, 4-ethyl. So here you see there is a branch, right? There's a branch. Here is also a branch. Here is also a branch. So these components are like this. It's just an example. Huh? It does not need to be only CH3. It can be CF3 or whatever it is. I'm just showing it for the purpose of branches. So this one does not have any branch. This is completely linear. But here it does have branch. You see, these are branches. And there are polymers which are cross-linked, right? Cross-linked. So those polymers will have a structure of, then maybe this carbon would be joined with this carbon. Maybe this and this will join. Okay, this will form like this, right? So cross-linked. It is linked in between that component, right? So there are different type of these fibers. Natural fibers actually are there. Okay. If you want to just check with the environment, you just those who live in singular regions, single areas, you guys should go and check with the Nava of, right, the bark of the Nava tree, right, bark of the Nava tree. And those who live in this Tamil area, you guys go and check with this papo tree, right? Papo tree itself, died papo tree. Okay, so there you will find these kind of cross-link structures. Those who have interest, just go and see. So single area people, you go and check with the Nava tree fiber and bark. Actually bark, fiber, it's not going to come as fiber. The bark you need to cut it and separate it to see. And those who live in Tamil area, you just go and see the papo tree, not living papo tree, a died papo tree. Okay, so they will have this kind of structures. Then I have network, right? So network, it is like high strength, right? So strength wise, this is first, this is second, this is third, this is fourth. So strength is decreasing this way, so the strength is increasing this way, direction of increasing strength. So from linear to branch to cross-linked network, it is strength is increasing this way, right? So network mean usually this phenolic content, benzene, other things, they all will form this network, right? So if you want to know what is benzene and all, I think I have already shown. But still, so these kind of things, right? This is a benzene, this is a benzene, right? Phenol, if I have an OH. So these kind of bonds, right? I'm not talking about this structure. You need to be very careful. I'm not talking about this structure. I'm talking about this structure, right? This particular bond. So this is actually C, 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 and C. 6 carbons are there. So this is the actual structure. So that for the easiness and standardness, we will write like this. Okay. This is actually this and this are equal. All right. And then we will have an H, right? We will have an H. All right. And then I will have a bond between this. Okay. So now you see, you check for each carbon. I will take example this carbon. Okay. 1, 2, 3, 4 bonds. Fine. I will take this carbon. 1, 2, 3, 4 bonds. Fine. I will take this carbon. 1, 2, 3, 4 bonds. So if you check any of this carbon, that will have 4 bonds, right? But the thing is, this double bond can be broken if it is necessary, right? But usually this double bond will not be broken right? And that's why they are high in strength, right? That's why they are high in strength. You see, than branched cross-linked are strength. Than the cross-linked network is actually strength. So this is the maximum strength, right? So this is the reason there are double bonds. If it is necessary, it can be broken, but usually it will not broken, right? So that's why strength is high for these type of molecules, right? These type of molecules. So there was a diagram I already show you about how will they take the shape, right? Yeah, so this is how it will take the shape, and I think, yeah, there's a piece. So this is the rough sketch of how will it look like. So now I am going to show the same thing in a 3D view, right? So just remember, these are carbon, right? These all are carbon, and these all are hydrogen, right? These all are hydrogen. Now here again, these all are carbon, right? These all are carbon, and this one is the physical area or physical volume which is covered by these 3 hydrogens, right? So one hydrogen would be here, one would be here, and the other one would be here, right? So this is a normal area which is covered, not area, sorry, volume which is covered by the polymer, right? So molecular orientation can be changed by rotation around the bonds, no bond breaking needed. So this is a linear kind of structure. If you bend it, that will bend, right? No problem. So if you just imagine a polythene bag, you can take a polythene bag, and if you fold it, that will be folded. No? So that's the thing. So they can be changing the direction without breaking the bonds.